All right, welcome everyone. Welcome back to Calculus 2. So last time we saw some applications of these series. So we finally are able to reap the benefits of talking about series for so long. We saw that we were able to approximate integrals that are either difficult or impossible to do. And we also saw how to evaluate like strange numbers, like for example, ln of 9/8, how do even computers do that? And the answer is through series. Now, what we're going to do for this week is we're going to find more power series for other types of functions as well. Because so far, all we have are rational functions, natural logs, arctangents, and yeah, that's pretty much it. So what we're going to do today, starting today, is we're going to try to find power series for any kind of function we want. Now, I got to offer a disclaimer here. You can't find a power series for every function. So there are definitely functions out there that don't have a power series representation. The good news is those functions are kind of esoteric and few and far between. So you usually don't have to worry about that. Most of the functions that you come in contact with will end up having some kind of power series you could write down. So I just want to offer that disclaimer. We can't use this for every function, but for most of the functions we encounter, it'll be fine. All right, so what are we going to talk about today? Lesson 27. This is going to be all about Taylor and Maclaurin series. Okay, so what are these right here? Well, let's start with a Taylor series, and then we'll get to a Maclaurin series. So a Taylor series is a series that looks like this. Let's say we want to represent a function, and pretty much any function we want, like I just said, as a series here. So f of x equals, and then we have the sum from n equals 0 to infinity. We have the nth derivative at a divided by n factorial, and then we have x minus a to the n. All right, now I need to clarify a few things here. First of all, what's this a number? A is a specific number called the center of the series. And the reason why this has the name the center is because this number is often the center of the interval of convergence. So for example, if you had an interval of convergence from -1 to 1, your center would be 0. And that would be this number right here. So it's literally in the center of our interval of convergence. Okay. Now, what is this right here? I don't know if everyone's seen this notation before. What does this parentheses and an n mean? The nth derivative at a can be written like this. And this is just where we take the derivative, whatever number n is, that many times, and then we just plug in a. So for example, like f2 of a would be f double prime of a. We just write this because if you're doing like the 14th derivative, you don't want to write like 14 little dash marks or whatever. So there's kind of this notation right here. And it's in parentheses to differentiate it from powers of that. Okay, so this is what a Taylor series is. So if we have any function, or pretty much any function, we could represent it as a series by finding out what all of these numbers are and then sticking them next to x minus a to a power. Now I want to talk about, oh yeah, and then finally, what's a Maclaurin series? A Maclaurin series is just a special type of Taylor series. It's a Taylor series where a equals 0. So rather than just having x minus a to the n, we're just having x to the n. And actually, most of the time, we're going to be talking about Maclaurin series because they're simpler, but most of what I'll say will also apply to Taylor series as well. Okay, now let's talk about this. Where on earth does this weird formula come from? Why do we have to take a bunch of derivatives of f? And why do we have to divide by a factorial? How will sticking this next to all of these x to a powers make a series that's equal to this function right here? It seems kind of strange. Well, let's go ahead and figure out where this comes from. And it kind of makes sense once you see it. So let's say I want to come up with a series. Let's just say I want a, oh yeah, I want a series for f of x. So I need to write it as some kind of polynomial. So I have n equals 0 to infinity. I have the coefficients for each x to a power, and then I multiply by x minus a to the n right here. Now, if I were to write this out rather than having it in sigma notation, this would be a0 plus a1 x minus a plus a2 x minus a squared plus a3 x minus a cubed and a4 x minus a to the fourth. And I think you get the picture after that. So my goal, I want to find out which coefficients I need to have in order for this to equal my function. So I want to find a formula for an. Because if I find a nice formula for an, I could just stick that in here, and then I have a series for any function that I want, which is nice because we saw the things we can do with series so far. Okay, so how am I supposed to figure out what a0, a1, a2, a3, a4? How do I know what all of these numbers are, all these coefficients? Well, to get a0, what I'm going to do is I'm going to plug in x equals a into this. And since it's the same function on both sides, then if I plug in a, it should be the same thing on both sides. So I have a0 plus a1, a minus a, plus a2, a minus a squared. And I think you get the point after that. Now, what's going to happen with all of these? Well, a minus a is equal to 0. So for all of these terms, except for this one, they're all going to go away. So I see that my a0 is just f with a plugged in. So I at least know what a0 is going to be right here. Okay, now let's say I wanted to find out what a1 is. I can't do the same thing because when I plug a in here, it's just going to be multiplied by 0. What I could do is if I take the derivative of everything, well, the derivative of a constant is 0. The derivative of this is just a1. The derivative of this is 2a2 x minus a. The derivative of this will be 3a3 x minus a squared, and then 4a4 x minus a cubed, and so on. Okay, so I took the derivative here, and that got rid of my a0, but that's okay because I already know what that is now. It's f of a. Now, let's say I want to know what a1 is. That's the next step towards getting all of these coefficients. I'm going to plug in a again. I have a1 plus 2a2 a minus a plus 3a3 a minus a squared. And then same thing over here, except to the third power. And then the same thing happens again. All of these are 0 because I just have a minus a for all of them. So I see that this time, if I want to know what a1 is, I just take the derivative of my function and plug in the center. So a1 is f prime of a. Okay, so we might be starting to see a pattern here. It seems like, okay, well, maybe a2 will just be f double prime of a, and a3 will be f triple prime of a, and so on. Let's see if that holds up. So if I do another derivative here, if I find out what f double prime is, well, let's see here. So the derivative of a constant is 0. For this, I'm going to have 2a2, and then I have 3 times 2 a3 x minus a, and then I have 4 times 3 a4 x minus a squared, and so on. So now if I plug a into here, then I just have 2a2. But that's interesting. This time we end up with a coefficient on our a2 here. So we need to divide that. So here it seems like we get f double prime of a over 2 is a2. So that kind of messes up our trend a little bit. It's not just f double prime, it's f double prime over 2. Okay, why don't we do one more of these, and then I think we'll see what the general pattern is overall. So let's do f triple prime, try to get a3. So we're doing the derivative of this. So we have 3 times 2. And then if I want, I can stick a times 1 in there without changing anything. I have a3. The next one, I have 4 times 3 times 2, a4 x minus a. And then I keep getting more of these x minus a's here. So if I plug in a for this now, and I know this is getting kind of tedious here, but this is the last one we need to do to see what's going on. We have f triple prime here. All of these are going to go to 0 like they did before. And we're just going to have 3 times 2 times 1, a3. But then we need to divide by this to get a3 on its own. So we end up with f triple prime over 3 times 2 times 1. Now, a more compact way of saying this is f triple prime of a over 3 factorial. And now I think we could see the pattern here. Kwong, what we're trying to do here is we're trying to find out what all of these a sub n are. Because if we can find out what numbers these a sub n are, then we have a series for our function here. So the way we're doing this is we're plugging in whatever the center is. So we have x minus something. We're plugging in whatever that is. And that will be 0 for all of these except for the constant term. So we keep doing that, and we're getting the equations for the first few of these in the sequence here. And we're trying to see if we can find a pattern. Now, it seems like the pattern here is that we have whatever n we're at with our an, we take that many derivatives, and then we divide by that factorial. So we're going to have our general pattern will be a sub n is where we take n derivatives, we plug a in, and then we divide by n factorial. So if we go back to the original equation, all the way up here, this is where that comes from. So this seems kind of random to show up in this formula up here, but there's a reason why this is here, and that's because if you want f of x to be a series, it needs to end up having this formula here by this reasoning right here. So this is where our coefficients for a Taylor series come from. That's where we get that kind of bizarre looking formula. Okay, so now that we see where that formula comes from here, what we're going to do is we're going to try to use this to come up with series for different types of functions. So from our first example, let's say we want to find a Taylor series, or rather a Maclaurin series, for f of x equals e to the x. We want to find a Maclaurin series. Remember, that's where a is 0. And we also want to find the interval of convergence. Remember, we need to find the interval of convergence so we know which x values are okay to plug into our series, because not all x values will work all the time. All right, so let's see here. Now, the way we find a Maclaurin series or a Taylor series for something is we keep filling out what these are right here until we can see a pattern. Once we see the pattern, then we can write out the formula for the series. So what do I mean by that? We're going to end up drawing one of these charts here. So we have a chart for n. We take the nth derivative of our function. We plug in the center for that, which is 0 in this problem. We divide this by n factorial. And then finally, we stick that next to x minus a to the n. Oh boy, this pen's days are numbered. We'll see if I could power through this, but I might need another one here. All right, anyways, let's figure this out. So let's do this for n equals 0 right here. So what does it mean to take 0 derivatives of a function? It just means you don't take any derivatives. So taking no derivatives of e to the x, well, that's just going to give us e to the x. All right, now what we do is we plug 0 into this e to the x. So we have e to the 0, which is 1. Then we do 1 over 0 factorial. And 0 factorial is 1, so this is 1. And then finally, we stick it next to x minus a to the n. But x minus a to the 0 is just a constant, 1. So this is just going to be 1. All right, let's do a few more of these until a pattern emerges. All right, so we do 1 derivative of e to the x here. So we have n is 1. We do a derivative of e to the x, but e to the x is probably the easiest function to do derivatives of because it's always going to be itself. We're going to get e to the x here. And since it's the same function, when we plug 0 in, we're going to get 1 again. Now this time our n is 1, so we do 1 over 1 factorial. But that's just going to give us 1 here. All right. Yeah, does anyone have a pen that they can loan me? I didn't expect this to die. So yeah, thank you, sir. All right. There we go. That's better. So then we have 1 times x right here. All right. Can you repeat the third one? Yeah, so this we just plug 0 into here, into our function that we got here, and then we just get 1 right there. All right, and then we have 1 times x here, or just x. All right, let's do 2. Well, the second derivative of e to the x will be e to the x. And then we plug 0 into that, it's still going to be 1. And then we have 1 over 2 factorial, that's 1/2. So our next term will be 1/2 x squared. So that's the next thing we're going to have here. Let's do one more, and then I think we'll see what's happening. So we do another derivative, but any number of derivatives of e to the x will be e to the x here. I plug 0 in for this, and I get 1, like that. And then I have 1 over 3 factorial is 1/6. So I have 1/6 x cubed. Okay, so I think we have enough information to see what's going to happen in the long run. So let's see if we can write down our series here. So we want to represent e to the x as our series. So we're going to go from n equals 0 to infinity. Now let's see here. It seems that whichever term we're on, we just end up having 1 over whatever that number is factorial. So here we have 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial. So it seems like the pattern is whatever n is, we're just going to divide by that factorial right here. And then we just stick x to a power next to it, x to the matching power. So it seems like our series for e to the x ends up being x to the n over n factorial. So this is going to be our Maclaurin series because it's centered at a equals 0, or e to the x. Okay, now we need to find the series interval of convergence. So it's nice that we have a series for this, but if it doesn't work for very many x, it's not that useful. So we need to figure out what x this is going to work for. So let's do the ratio test right here. So we have the limit as n goes to infinity of absolute value of x to the n plus 1 over n plus 1 factorial. And then we have n factorial x to the n. All right, so these will cancel out and give us an absolute value of x. These will simplify, n plus 1 factorial and n factorial, and give us an n plus 1. All right, I think we've actually done the ratio test on this exact series before. What is this limit going to end up being, no matter what value x is? It's going to be 0, right? Because technically this absolute value of x can move out of the limit. And then this is equal to 0. Now remember, the whole goal of the ratio test is to be less than 1. So, well, no matter what x we plug in, we're always going to get 0 for the ratio test, right? So it doesn't matter which x we plug in at all. It's going to converge for all of them. We're going to get 0 for all of them. So that means that the IOC here is going to be all real numbers. All right, that's actually really nice. So we not only have a representation of e to the x as a series, but it works for any x we want to plug in. So we can plug in x equals 100 million, and we don't need to worry about this series diverging right here. So we have a really nice interval of convergence. So this is an excellent series right here. All right, now I want you guys to give a shot, take a crack at this here. So I want you guys to kind of use the same methodology, try to make one of these tables here. But for you guys, I want you to do the function f of x is cosine of x. and I want you to find the interval of convergence once you're done with that. So try to do the same thing that we did up here for cosine of x. And I'm going to give you a hint for this one because this one's a little bit trickier than the previous one. So here's a hint. If you want to skip even terms, or sorry, odd terms, use 2n instead of. You'll know what I mean by this once you start working on the problem. I'll give you guys a few minutes to take a look at this. Oh, sorry, I didn't specify that. Yeah, thank you. So our A is 0 for this. We want to find a Maclaurin series. And don't worry, we'll talk about some non-zero A's later on. All right, another minute or so, and then we can talk about it. you after making the chart, you try to find a pattern, especially pay attention to this column. Try to see what the pattern is with these numbers and then write down a formula for that pattern. And pay attention to the hint. Again, I would go to maybe n equals 4 with this one to see what's going on with the pattern. But we'll talk about it in a second. All right, let's see what's going on with this. And you can feel free to keep working on it if you feel like you're getting somewhere. All right, so let's draw our chart here. We're going to plug in 0 because that's our A. All right. So let's see here. Let's start n equals 0. So if we take no derivatives of cosine, that's just cosine. And if we plug in cosine of 0, or we plug 0 into cosine, we get 1. We have 1 over 0 factorial is 1. So we just end up with 1 as our first term right here. All right. Next, let's do one derivative of our function. So one derivative of cosine gives us negative sine of x. And then if we look at negative sine of 0, well, that's 0. So that's actually kind of funny because then we do 0 over 1 factorial is 0. And we do 0 times x to the first power is 0. So it seems like we're going to skip this n equals 1 term. We're not really having much of anything here because we get 0 for that. All right, let's continue on to 2. We have the derivative of negative sine of x will be negative cosine of x. We have negative cosine of 0 is negative 1. So we have negative 1 over 2 factorial. So this gives us minus 1/2 x squared when we evaluate that. All right, I want to do maybe 2 more, and then I think we'll start to see the pattern emerge here. Okay, so let's do the derivative of negative cosine, and we get positive sine of x. But then sine of 0 is once again 0. So we have 0 over 3 factorial, but that's just 0. So we don't end up having a cubed term here. And then finally, we do the derivative of sine, and we get cosine. And notice that we actually kind of come full circle here. If we do 4 derivatives, we end up back where we started. So it seems like there's going to be some kind of repeating cycle here. So we have cosine of 0 is 1. This will be 1 over 4 factorial. So we have 1 over 4 factorial x to the 4th. Okay. And I think this here should probably be enough information for us to maybe spot a pattern here. And I think there's actually a few different patterns going on if we pay attention. So what's one thing we notice about this? Well, one thing we notice is that we don't have any odd powers of x, because it seems like every time we get to an odd derivative, we end up with sine, and then sine of 0 will be 0 right here. So it seems like we want to skip all of the odd terms and only have even ones. Now, this is where the hint comes in. If I want to skip odd terms, then I could just use 2n instead of n. And why is that? Well, 2n will always be even. 2n is always an even number here. So let's try to write our series. So first of all, it seems like we're going to have x to the 2n. And this is because we only want to have even powers of x. All right. So we have that. It also seems like we're always dividing by an even factorial. We're never dividing by an odd factorial, we're only dividing by even factorials. So I'm going to divide by 2n factorial down here. And notice that the power of x always seems to match the factorial. So that works out here as well. Now there's one more thing that's going on with this? What's one more pattern that you guys can see here? This is a what type of series? Yeah, that's right. It's going to be an alternating series because we have positive, negative, positive. And if we went to 6, we could see that it's going to be negative again because we would get negative cosine x. So we're going to stick a -1 to the n in here. Now, some people ask, oh, why don't I do -1 to the 2n? Well, if I do -1 to the 2n, -1 to an even power is always just 1. So it kind of destroys the alternating effect if we do -1 to the 2n here. So I'm just going to leave it as -1 to the n. And that's it. That seems to be all that's going on here. So we have only even terms. We divide by even factorial, and it's alternating. So this is going to be our Maclaurin series for cosine of x right here. And this is kind of a useful lesson in general. If you ever have even terms, only even terms in your series, use x to the 2n. And I bet you could guess how it would work with odd terms. If you only want odd terms in your series, use x to the 2n plus 1. This 2n plus 1 will always be an odd number. Now remember, a series is only as good as our interval of convergence. All right, so let's figure out what the IOC is here. All right, so we have -1 to the n plus 1. And then if I plug in n plus 1 next to this 2, it'll be x to the 2n plus 2. And then we divide by 2n plus 2 factorial. Then I have the reciprocal of the original right here. At n equals 2, wouldn't that make it positive? Oh, that's a good point. So when we do this 2n thing, we kind of redefine what n is. So you can almost think of this as like the old n up here. And then when we do x is 2n, we almost have a new n, where this new n starts at 0 here, and then we have 1 here, and then we have 2 here. And you can kind of see that because if you plug in 0 into this, you'll get 0 for all these. If you plug 1 in, that will get doubled, and you'll get 2 and 2. If you plug n equals 2 in here, that will be doubled to 4, and so on. Yeah, so that's effectively what's happening here when we do this this 2n thing. All right. So let's see here. Let's see what's going to happen with this ratio test. Oh, oops, I forgot x to the 2n. All right, so we're inside absolute values. So these negatives don't really contribute anything. Let's see, actually everything else is positive as well because we have x to an even power, x to an even power, and factorials. So I guess we don't need absolutes right here. Why can you not keep the odds? Well, we don't want any odd ends because all those will just end up being 0 right here. So that's why we decided to skip the odds for this one. All right, so let's see how this simplifies. This is 2 powers bigger than this right here. So this will just be x squared. And I think we've seen this before, how 2n plus 2 factorial cancels with 2n factorial. We have 2n plus 2 times 2n plus 1. And then using the same reasoning as our last ratio test, we can move this out. All right. And then this is going to end up being 0. And then once again, we get that same situation that we had before, where we get 0 for the ratio test, no matter what our x is. Because 0 is going to be less than 1 no matter what x is. So once again, we actually have a really nice interval of convergence. It's going to be all real numbers. So once again, we could plug in any number we want into this series, and it will converge. Why don't you want the zeros in the series? Well, adding 0 doesn't really contribute anything. So we can kind of just skip that. So that's why we don't want the zeros. All right. So we found a series for e to the x. It's the sum from n equals 0 to infinity of x to the n over n factorial. The IOC is all real numbers, which can be written like this kind of R with an extra bar right there. We just saw what cosine's Maclaurin series was. We have -1 to the n, x to the 2n over 2n factorial. And the IOC for that was all real numbers. And for sine of x, so we have sine of x, that's the sum from n equals 0 to infinity. So it's very similar to the cosine one, except this time x is going to be the 2n plus 1 instead. You may remember from algebra or trigonometry class in high school that cosine was referred to as an even function and sine was referred to as an odd function. That's not a coincidence that cosine only has even terms and sine only has odd terms here. It has to do with that terminology as well. Would the series be equal to this one if you included them? Yeah, but it'd be harder to write a formula for that because you'd have to do some kind of like piecewise thing where you'd say for any even n, we get this, and then for any odd n, we would get 0. But if you wanted to write it that way, yeah, there wouldn't be anything wrong with that technically. All right, and then finally from before, we have a few other series, but all of those series come from 1 over 1 minus x, which has the simple formula x to the n. The trade-off with this, though, is that the interval of convergence is limited to -1 over 1. And these series are what I like to call the big four right here. We can get pretty much any other Maclaurin series that we want by manipulating one of these. So as you kind of saw, doing that table is not really that fun. It kind of takes a lot of work to do that, and then you have to spot the pattern. But the good news is that if we use the big four right here, we can often find the formulas for other series without that much work by substituting in. And we already saw how to do it with 1 over 1 minus x. We already saw how substituting in or making things look like 1 over 1 minus x can give us other series. Well, it turns out that we could do the same thing with e to the x, cosine of x, and sine of x as well. We can also use those in substitution to get more series. So let's see here. So as an example of this, oh, by the way, you guys don't need to directly memorize this. So for exam 3 and the final, you're going to get an equation of common Maclaurin series with their IOCs. And it's going to include all 4 of these. And then it's also going to have the one for arctangent and the one for log as well. So don't sit at the paper just staring at this because you're just going to get one of those. Although honestly, if you use these often enough, you'll just memorize them for free. All right, so I want to use the big four, or at least one of them, to find a Maclaurin series for 5 to the x. And we also want to find the IOC too. Okay, so how will we get a series for 5 to the x? Well, one way is we could make one of those tables. So we can make a table, we can take a bunch of derivatives of 5 to the x and see if we can spot a pattern. And with this particular function, it's actually not too bad to do that. The pattern is relatively simple for this. But even if you know what the pattern is, even if it has an easy pattern like e to the x, we see that it can kind of take a while. So what I'm going to do instead is I'm going to recognize that 5 to the x is the same thing as e to the ln of 5 to the x. Because e to the ln of 5 is just a very fancy way of writing 5, right? Now, by exponent rules, if I have an exponent and then that's raised to an exponent, I can multiply them. So I have e to the ln of 5 times x right here. So 5 to the x is e to the ln of 5 times x. Now, I know what the series for e to the x is, so it's not too much of a leap to get a series for e to the ln of 5 times x. All I need to do is replace the x in here with an ln of 5 times x instead. And just like that, in pretty much no time at all, we end up with a series formulation for 5 to the x right here. So no table necessary. We didn't need to do any of that. We just substituted into a known Maclaurin series, and that gave us this right away. All right, and then we could also do, we could also use the existing IOC to help us as well. So the IOC with all real numbers, that's the same thing as negative infinity is less than x is less than infinity, right? Those are saying the same thing. Now, what I'm doing for this problem is I'm replacing this x with an ln of 5 times x, right? That's the only thing I'm doing. differently. Now, what I could do is I could divide both sides by ln of 5, and infinity divided by any number is going to be infinity. So negative infinity over ln of 5 is infinity, and then we have infinity over ln of 5 is infinity. So it seems like we have the same IOC. It's going to be all real numbers, even for the 5 to the x1 as well. If you're not comfortable doing this, though, that's totally fine. We could also have used a ratio test here, but that also would have just given you negative infinity to infinity. So using the existing Maclaurin series is often a desirable alternative to doing things from scratch. So kind of in the same way that we just did this one right here, why don't you guys find the Maclaurin series and IOC for sine of x squared. So see if you can find a series representation for that one, along with its interval convergence. All right, I need to make sure we have time for our last example here. So I'm just going to go ahead and reveal the solution for this. So sine of x written above is n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So all I'm doing to get sine of x squared here is I'm simply replacing any x I see in this formula with an x squared. So sine of x squared's got to be equal to the sum from 0 to infinity, negative 1 to the n, x squared to the 2n plus 1. But then this time we see that we have our exponent rules here. So this power is just going to be 4n plus 2 right here. So this is negative 1 to the n, x to the 4n plus 2 over 2n plus 1 factorial. Now notice that this doesn't change. It's still 2n plus 1 factorial. The only thing that changed was the x here. All right, and then what we're doing here to find our interval of convergence is we're seeing which x's will allow x squared to be in between negative infinity to infinity. Now, if you want a square of a number to be between negative infinity and infinity, you could plug in any number you want. So this is the same thing as saying this right here. So the IOC is all real numbers, because if you square any number, it's still going to be between negative infinity to infinity. So our IOC will be all real numbers for this as well. And usually if the IOC for the base series is all real numbers, the IOC for the modified series will also be all real numbers. That's not 100% of the time the case, but it is most of the time. All right. Now let's see here. Well, my last example, so all of the series we've constructed so far have been Maclaurin series, meaning their centers are zero. But I also want to show you how we would find a Taylor series for sine of x centered at a is pi over 2. So I want to do at least one of these with a non-zero center. And it's not really too much different, but I just want to make sure that we have some exposure to this. So we have the nth derivative at x, the nth derivative at pi over 2 this time, the nth derivative of pi over 2 over n factorial, and then the nth derivative of pi over 2 over n factorial times x to the n. Okay, so let's see. Let's do this real quick. All right, so no derivatives of sine will be sine. Then we have sine of pi over 2, which is 1. We have 1 over 0 factorial, which is 1. And then x to the 0 power is 1. So it looks like we just get 1 for this. All right, the next, our derivative of sine yields cosine. Now cosine of pi over 2, that's going to be 0. So we have 0, and then we have 0 for this right here. We do the derivative of cosine, we have negative sine of x. So we have negative sine of pi over 2, which will be negative 1. Now this seems kind of familiar, right? I think we've seen this before. Okay. If we do 3 right here. Oh, should the last column be x minus a? Yeah, that's right. Yeah, this goes to show you how often I do non-Maclaurin Taylor series. I usually just do Maclaurin series. Sorry, this should be x minus pi over 2 to the end. Oh, so this should be as well. All right, let's do maybe 2 more, and I think we'll for sure know what's going on. Cosine of pi over 2 is once again 0, meaning that these will be 0 here. And then I bet without even filling in the chart, you guys could probably guess what this is going to be here. What do you think this term is going to be all the way out here based on what's going on here? Yes, we have 1 over 4 factorial, or 1 over 24. And then what else? X minus pi over 2 to the 4th. Absolutely right. And in case we didn't see that, we would do a derivative here and get sine. Sine of pi over 2 is 1. We have 1 over 4 factorial, and then we would get this here. All right, so this is extraordinarily similar to the pattern that we saw earlier. So let's summarize here. We only want to have even terms, so our x to a power is going to be 2n. And this time we do x minus the center. So we're doing x minus pi over 2 to the 2n here. We're going to divide by 2n factorial. And then just like the series earlier, this is going to be alternating. So the series for sine of x centered at pi over 2 is different from the Maclaurin series. So if we go back up here, the Maclaurin series only has odd terms, but then this Taylor series centered somewhere else only has even terms. So this goes to show you that recentering your series can drastically change what the formula looks like. Okay, and then the IOC for this is all real numbers. We could use the ratio test to do that. Now I want to say one more thing about this. So earlier, we had a series for sine of x, right? So we had this Maclaurin series centered at 0, and this series perfectly represents sine of x for any x value whatsoever, because the interval of convergence is all real numbers. Now, given that information, why would we want another series for sine of x? We already have a perfectly good one centered at 0. So why did we need to bother making one centered at pi over 2 if the interval of convergence is all real numbers anyway? We just already have plugged in any number we want. And the reason is it has to do with what we were doing last class. The closer to the center of a series you are, the better it is at approximating. So yeah, maybe if we wanted to do like sine of 1/2, this one would be better. But if we want to do like sine of, like, what's a number close to pi over 2? Like sine of 2, which is closer to pi over 2, then this would be the better series to use here. So the closer you are to the center, the better the approximations you'll get if you use the series to approximate stuff right here. All right, that's about it for today. So now that we know how to find more general types of series, next time we're going to look at more stuff we can do with them. And next class, we're going to cover, for those of you who are interested, why the sum of all the positive whole numbers is -1/12, or supposedly at least. So yeah, we'll be talking about that next time. And yeah, I'll post the lecture for last class sometime this afternoon.
Can you